So far, we have been taking our derivatives using the definition of the derivative. There's steps, it's a process, you have to do a lot of algebra, sometimes it's lengthy. And as we move forward, that process is going to get pretty ugly depending on our derivative. But luckily, as we go through that process, or people have in the past, they've ended up recognizing patterns. So based on these patterns, we actually have these derivative rules that we can use instead of using the definition. We still need to understand the definition, how it works, what it's asking, but now we're going to have these little shortcuts that are going to help us take our derivatives faster. So I've got us kind of set up just to kind of go through our first rules, and then we'll put those to practice. So, excuse me, the first thing I want to talk about is this notation, so our d dx. What this is the operation of take the derivative. So when we see the d dx in front of any function, that notation is just saying take the derivative of whatever that is. Okay, and that's how I have it set up here. So let's go through some of these rules. This first one is d dx k, where here k is any constant number. So k could be 2, k could be pi, root 2, whatever it is. K is just a number. So again, if I were to look at an example, what is the derivative of 3? The slope of 3. If we were to look at that graphically, 1, 2, 3, this is just a horizontal line at y equals 3. What's the slope on that thing? It's flat, no slope. Anytime you take the derivative of a constant, that derivative is equal to 0, which is nice. We like taking those derivatives because they just kind of disappear. Sorry, having a little hard time talking this morning. All right, so first rule, the derivative of a constant is 0. Okay, then we have x, the derivative of x. Anytime we look at a line, so if you guys remember y equals mx plus b, m is the slope of that line. X is to the power of 1. So anytime you have x to the power of 1, you're looking at a line. So the function itself is telling you the slope. So here, there's a 1 on my x, so the derivative of x is just 1. Okay, that one's pretty easy. Nice. Okay, then we have the derivative of x to the n. This is our power rule. We've seen this in action a couple times when we've been doing our definition of a derivative. So we've seen it, but now we're going to actually just use this shortcut. It makes our lives so much easier. For example, if we were to take the derivative of x to the 18th power, if we were using the definition, that would mean we would have to multiply x plus h together 18 times. Hard pass. No one's going to do that. But with the power rule, after doing the definition a million times, we've seen this pattern where the derivative of x to the 18 is 18x to the 17th. So what I'm going to do is I'm going to drop my power, 18, and then I'm going to subtract 1 from the exponent. That's our power rule. So x to the n becomes n times x to the n minus 1. Power rule. Okay, we're going to put that into action here in a couple minutes when we look through some examples. All right, moving on. So we've got 1, 2, 3 rules. Here's my fourth rule. This is called the constant multiple rule. The constant multiple rule, when I take the derivative of a function, f of x, but it's being multiplied by some constant. The cool thing is the constant's just going to come with us, and we just take the derivative of whatever that function is. So, for example, if I were to use the power rule, but I have 3 times x to the 10th. 3 is the constant multiple, x to the 10th is my function. So I'm just going to carry the 3, and then I'm going to take the derivative of x to the 10th, which is 10 x to the 9th, which then ends up giving me 30x to the 9th. So all I'm doing is just carrying that constant with me, multiplying it by my derivative. Pretty straightforward on that one. Okay. Here, this is the sum and difference rule. This is kind of similar to the rules we've talked about with limits. Is you can split it and take the plus or minus. You can do each function individually, or you could do them at the same time. It's going to give you the same solution. So here we have a function h of x that is made up of two separate functions, f of x and g of x. It could either be a positive or a negative here. I'm just using them at the same time because the same rule applies. So when I want to take the derivative of h of x, what I'm doing is I'm taking the derivative of f of x plus or minus g of x. All I have to do, I could do this individually, so I could split this and take the derivative of f of x by itself, and then take the derivative of g of x by itself. It's going to give me the same solution, right? So here, h prime of x, so the derivative of h of x, is just equal to f prime of x plus or minus g prime of x. To me, this one's kind of a g, like that makes sense, that's obvious. Just take the derivative of each individual piece, and that is still the derivative of the full function. Okay, and if you were in class, we talked about this one. I went through the definition to prove it, the derivative of e to the x. We went through, we showed how it worked, we showed what it was, but for now, I'm just telling you so you know how to use it. The derivative of e to the x is e to the x. So, we're going to use these derivatives in some examples, so take a look.